describing the distribution of p hat. Now, a random sample of 100 names is drawn from the electoral roll. Let p hat be the sample proportion of females in samples of size 100. So we're going to investigate the expected value of the random variable p hat, the standard deviation of the random variable p hat, and we're going to compare the spread of the distributions of p hat for n equal to 20 and n equal to 100. So I'll start, first of all, by carrying out a simulation. So similar to the one that I did in the previous video on the distribution of sample proportions, I'm going to carry out the simulation and I'm going to capture the values in a spreadsheet. So I'm taking a sample of 100, and this line here gives me the mean value of all of the samples. So I repeat the sampling, another sample of size 100 and another one. So I keep repeating the sampling with samples of size 100. And I build up a distribution of p hat. And as we saw in the previous video, the mean value of all of my point estimates of lowercase p hat all converge towards the true population proportion, which is 0.5. In this case, in this simulation, from repeating the sampling 200 times, it's 0.4982, very, very close to the true population proportion of 0.5. So from the simulation, we observe that for repeated sampling, the mean of the sample proportion p hat tends to the true population proportion p. And we can use some algebra to get that. So on the formula sheet that you get with the exam, you will see that the expected value of the random variable p hat is equal to p. And that comes from some simple algebra. Because x is normally distributed, its expected value is n times p. So the expected value of p hat is the expected value of x over n. So replacing n times p for the expected value of x, the n's cancel, and we get the result that we observed from the simulation, that the expected value or the mean value of the distribution of sample proportions is p, the true population proportion, which is why sampling is valid. So the mean is simply going to be 0.5. Right, so the standard deviation. Now, the standard deviation is a measure of the spread of the distribution, and once again, from some algebra, we can derive that formula as well. So because x is binomially distributed, the variance of x is np times 1 minus p. If I substitute that for the variance of x, one of the n's cancel, and I get, when I cancel the n, I get that the variance of p hat is p 1 minus p over n. So the standard deviation is the square root of p 1 minus p over n. So that's where that formula on the formula sheet comes from. So in this case, p is 0.5, n is 100, and this is one that you can do in your head. Substituting those values, we get 1/4 at the top and 100 on the bottom, so it's going to be 0.05. Now, comparing the spread of the sampling distribution of p hat for n equals 20 and n equals 100. So we're going to do a simulation this time where we're going to change the sample size from a small sample, only 10, through to 250. Okay, so this time I've got 200, so I've repeated the sampling 200 times. So I've got samples of size 10, 1 to 200 times. So that's what this dot plot is showing. If I press this, I get a different 200 samples of size 10. Okay, now I'll increase the sample size in this simulation and observe the spread. So 20 this time, sample size of 20, 30, 40, 50, 60, 70, and so on. And it's quite obvious from the simulation that as the sample size increases, the spread of the sampling distribution of p hat decreases. So for a given value of p, the spread and the symmetry of the distribution of p hat depends on the sample size n. So the spread decreases as the sample size increases and the symmetry increases. Now, we weren't able to see that in that simulation, but if we rescaled as we increase the sample size, we would observe that it actually becomes more symmetrical. And we expect the spread to decrease as n increases because the standard deviation has n in the denominator. So as n increases, the 1 on n has to decrease. So as n approaches infinity, the standard deviation approaches 0. So this brings us to the idea of what about a probability model for the distribution of p hat? So describe the shape of the distribution, explore a suitable model, and under what circumstances is this model a good fit. So this time, we've already seen the effect of changing n. Now let's have a look at the effect of changing p. So as we change p, if we keep n the same and we change p, we see that the spread gets less. So the spread is greatest when p is 0.5. And for values, as we move away from 0.5, it becomes less symmetrical. So a symmetrical model doesn't work quite so well if we have fairly extreme values of p, close to 0 or close to 1. And we change the sample size as well. See, it's not quite as asymmetrical when we have extreme values, but it's still not a nice symmetrical model the way it is at 0.5. So what might here I've got the same with a histogram. So what might a good model be? Well, let's investigate a normal distribution to model the distribution of the sample proportion. This time I've got n equal to 40. So while I've got the histogram, I can go to Menu and Analyze, and number 9, Show Normal PDF. We see that that's quite a good fit. That's actually not bad. Let's go back to the dot plot. The other thing I can do, I can control Menu on a dot plot, and one of the options is Normal Probability Plot. So normal probability plot, what it does is it shows the expected value that you would get if it's a true normal random variable against the actual value. So if it's a perfectly normally distributed random variable, every point should be on the line. Now we see that at the extremes, it's not a very good fit. But near the center, it's actually very good. There isn't a lot of variation away from that line. So the normal distribution works pretty well. And here we get a different picture. We see that the normal probability model is also quite a good fit. So the approximate normality of the distribution of p hat. So the normal distribution can be a suitable model under certain circumstances. Now both n and p, as we saw in the simulations, influence the approximate normality. Now as a guide, what many statisticians use is that for the normal distribution to be valid, the sample size needs to be such that it contains at least 10 successes and at least 10 failures.